All antiepileptic drugs, or AEDs, currently available can be grouped into 4 broad classes based on their different mechanistic targets: presynaptic voltage-gated ion channels, presynaptic neurotransmitter release machinery, the GABAergic system, and postsynaptic glutamate receptors. Currently marketed AEDs do not selectively target postsynaptic glutamate receptors. However, AEDs that directly affect presynaptic targets may actually have their ultimate action by indirectly suppressing glutamate release, thereby reducing postsynaptic excitatory neurotransmission. The mechanisms involved in the generation and spread of seizures converge upon a common neuronal pathology in which excitatory postsynaptic glutamate receptors play a key role. Glutamate, the primary excitatory neurotransmitter in the brain, binds to 3 types of receptors. These glutamate receptors are known as AMPA, NMDA, and kainate. Glutamate binding to these receptors results in a postsynaptic excitatory signal called the excitatory postsynaptic potential, or EPSP. In normal neurotransmission, an EPSP is a depolarizing postsynaptic signal related primarily to activation of AMPA receptors. AMPA receptors are responsible for the fast initial component of the EPSP, which mediates the majority of normal excitatory transmission by glutamate. In contrast, NMDA receptors mediate the slow component of the EPSP and are mainly activated upon AMPA-initiated depolarization. Glutamate transmission is involved in the pathophysiology of epilepsy in that excessive glutamate release has been observed during seizure activity in humans. This excessive glutamate release binds to both AMPA and NMDA receptors, leading to an abnormal epileptic discharge called the paroxysmal depolarization shift, or PDS. AMPA receptor activation initially triggers the PDS, while NMDA receptor stimulation maintains this signal. The binding of excessive glutamate to AMPA receptors triggers the PDS, an important marker for seizure activity in the brain. AMPA receptor antagonists have been studied in many animal models of partial and generalized seizures. These compounds act on AMPA receptors to reduce excessive excitatory neurotransmission that occurs in epilepsy. AMPA receptor antagonists act mainly by 2 different mechanisms. A competitive antagonist binds to the glutamate binding site and prevents glutamate from binding, thus preventing receptor activation. However, a non-competitive antagonist binds to another site on the receptor. This binding still allows glutamate to bind, but receptor activation is prevented. In the presence of high glutamate concentrations as seen in seizures, competitive antagonists may be displaced from binding. In contrast, non-competitive antagonists could inhibit AMPA receptors, even in the presence of high glutamate levels. Current AEDs affect a variety of molecular targets and mechanisms in the brain. Advances in our understanding of the pathophysiology of epilepsy, along with molecular targets of AEDs, provide an opportunity for the development of new antiepileptic therapies.